A huge thanks to my Patreon supporters for making this episode possible. Good morning, fellow mathematicians! Welcome back to another video. We are going to do some physics today again, or engineering, or whatever. Applied mathematics. We are going to apply the Laplace transform to a physical system that I have talked about in the last advent calendar, I think. So it has been a year ago. I was planning on doing Laplace transforms on physical systems for 2 years by now, and finally I get around doing so, and it's going to be quite good if you ask me. It's a lot of fun applying Laplace transforms to systems like this. And the system we are going to talk about is the following one, namely phi double dot plus our boy g divided by L times the sine of phi is equal to 0. And you might recognize this as being just a differential equation which describes the motion of a simple pendulum swinging around. And we are going to turn this into the harmonic approximator today, because this right here doesn't really allow for a very nice solution, and using Laplace transforms is even harder on this thing. So we are going to say that phi is really small. Okay, basically I'm really small, meaning we are going to get rid of our boy the sine right here, turning all of this into the harmonic approximator. The video I'm referring to you can find down there in the description, and we're going to apply the Laplace transform to this thing after a tiny little PSA here, because this video has been sponsored by The Ridge, your source for the high quality wallets that I'm presenting here on this channel from time to time, and they are really high quality, extremely durable. So a short and spicy introduction about our today's sponsor. They're basically providing you with daily life essentials like their wallets, okay? They right here are their flagship products, or my new most favorite products on their website, their backpacks. They are absolutely amazing. I love those. I have talked extensively about the backpack last week, and I already made an Instagram post, and I love this thing. It's weatherproof, it's amazing, you can charge your phone, etc. It's absolutely fabulous. But we are going to focus on the wallets today, because they actually swear on one thing. Okay, this right here, this Ridge wallet is going to have a lifetime warranty, all of their Ridge wallets. They swear on the durability of their products, and if it's ever going to break, which it's not going to break, trust me on this one, you can just refund it. You can throw it back their way, and they are going to give you a full refund on the product. Lifetime warranty on this absolutely durable, absolutely stylish, industrious, sleek looking thing, which comes in many different colors, including burnt titanium. And if you still don't trust me on how great this product actually is, I invite you to check out their over 30k 5-star reviews. They get all over the place. Amazon, their website, Google, etc. All of them are going to tell you the same thing. Looks good, does a great job. You can fit a bunch of credit cards in here. Even a money pocket is here at the back, and it's just going to change your pocket situation overall. So if you want to try it out, if you want to support the channel, make sure to check out the link at the top of the description, rich.com/PapaFlammy. Oh, this just rolls over the tongue. It's so amazing. PapaFlammy, you can use this code at checkout too. You're going to get 10% of your whole order, including free shipping, which is absolutely amazing. So try it out and support the channel this way. Ridge wallet, pretty good stuff. And now we are going to dive into the main video. Namely, we are going to apply the Laplace transform to this thing. And if you're not yet familiar with Laplace transforms, just take a look into the description. There will be a link to the whole Laplace transform playlist with all the essentials you need to solve the problem we have at hand today. So at first we're going to apply the Laplace transform to both sides. Meaning Laplace transform is being denoted by this very sexy looking L. Okay, this thing is absolutely thick. Okay, it's a thick freaking L. And phi double dot, which is our angle, okay, second derivative with respect to time of our angle, plus g divided by L, where g is the gravitational acceleration pi squared, e squared, and L is the length of our pendulum strings, okay, times phi is equal to the Laplace transform of 0. So we have learned that the Laplace transform of 0 is nothing but 0, because Laplace transform is being defined by an integral, okay, and the kernel of this thing is just 0 basically overall. So this right here holds. And now we are going to apply the Laplace transform to each and every part here, because we have learned that the Laplace transform is actually linear. Since it's an integral, it's also linear. Meaning we can say the Laplace transform of the addition of this thing is the Laplace transform of the first thing plus the Laplace transform of the second thing. Now we are going to make use of our Laplace transform table that we have basically derived on this channel extensively 2 years prior to the making of this video right here. That right here is actually equivalent to saying, okay, we are going to have s squared times capital F of S, where capital F of S is the thing that we want to solve for in the process, and then we are going to apply the inverse Laplace transform to the whole equation then. And then negative S times, okay, our regular phi with respect to 0, it's the solution to the initial value problem. So phi of 0 minus phi dot of 0. Okay, this right here is basically the angular velocity at the point t being equal to 0, is hence equal to, no, we are not done yet, we also have to add g divided by L plus our Laplace transform of phi, and Laplace transform of phi is just basically capital F of S. And not plus, but times is hence equal nothing but 0. Okay, this right here is what we are going to have now. Also, I would like to give g divided by L a new name. If we do some dimension analysis, you might notice, okay, meters per square second, okay, is our g. Also, our L is nothing but meters in units. Meters divided by meters is 1. So this thing right here has units of 1 divided by second squared, and this basically is just the eigenfrequency of the system but squared. We are going to call it omega null squared. This is what we are going to have now, and now we are going to solve for our capital F of S. Everything else goes to the other side, so we are going to add this part to the other side and this part to the other side, and also we are going to factor our capital F of S out, leaving us overall with, okay, we are going to have S squared plus omega null squared, omega naught squared, times capital F of S, being hence nothing but S times phi of 0 minus phi dot of 0. Okay, this right here, with a positive sign, is going to be what we are having now. We want to solve for F of S, capital F of S completely. So we are going to get back from the, this right here should be the frequency space, back to the time space. Okay, we are in the frequency space right now. We want to get back from the frequency space to the time space, meaning we're going to divide both sides by S squared plus omega null squared under the condition that's not equal to 0. It's not equal to 0 by the conditions that we have basically implied on our Laplace transform that we can do under those certain conditions. Okay, so we are going to divide both sides by S squared plus omega null squared. This and that is going to cancel out, dividing both sides by this. Now we can actually break this up, meaning our capital F of S is hence nothing but S divided by S squared plus omega null squared times phi of 0 plus, and now we are going to have 1 over S squared plus omega null squared times phi dot of 0. And now what we are going to do is we are going to apply the inverse Laplace transform on both sides. If we were to apply the inverse Laplace transform on both sides, the inverse Laplace transform of capital F of S is going to be phi yet again. This is what happened before. We applied the Laplace transform to this part right here, and we got g divided by L times F of S. And now we want to get everything back from the frequency space to our time space. Meaning if we were to apply the inverse Laplace transform to F of S, we are going to get phi of t out on the other side. This is what we want to have. Also, we are going to apply the inverse Laplace transform to this whole thing. Inverse Laplace transform is defined by a contour integral. Since it's an integral, it's also linear yet again, meaning that's equivalent to saying we are going to have the inverse Laplace transform of S divided by S squared plus omega null squared. Also, phi of 0 is going to be the solution to an initial value problem, meaning it's a constant. And since this right here is an integral operator, it's linear, meaning we can bring the constant to the outside. So this inverse Laplace transform times the solution to the initial value problem plus the inverse Laplace transform of what we have here, 1 over S squared plus omega null squared, and once again times the solution to the initial value problem. Okay, that was a lot of writing, but this is what we are having now. Our phi of t is hence nothing but this right here. Okay, we don't care about this part right now. All we care about is the inverse Laplace transform of those parts. And now we are going to make use of identities yet again, because we have actually identified what the Laplace transform of the cosine of at and Laplace transform of the sine of at actually is. And then we can just apply the inverse Laplace transform on both sides, and then we are done. Quick little reminder, if we have the Laplace transform of the sine of at, what we are going to get out on the other side is hence nothing but a is a constant which is going to be Doesn't matter, it's element of the real numbers, I suppose. A divided by s squared plus a squared, and the Laplace transform of our cosine of at has been nothing but s divided by s squared plus a squared. And now you might see the similarities if we were to apply the inverse Laplace transforms on both sides, especially for the cosine. You're going to notice that this part right here is exactly the cosine of, and what is our a in our example right here exactly? So we got a squared down here, so by comparing coefficients, our a is nothing but omega naught. Meaning overall, our phi with respect to t is hence nothing but, okay, we are going to get phi of 0 times the cosine of a times t, where our a is nothing but omega naught, times t, plus. And now here is where it's going to be a little silly-squilly, okay? That's the thing about Laplace transforms. You have to do a lot of manipulations, algebraic manipulations all the time. So in order for us to get a sign out on the other side, on this part, what we would need up here is our a yet again, which is nothing but omega naught. How can we get the a up here in the numerator? Well, we are going to expand this fraction by omega naught over omega naught. And since omega naught is a constant, we can bring the 1 over omega naught to the outside. Meaning overall, what we are going to do is we are going to multiply this fraction with omega naught, but we are also going to divide this fraction by it, meaning we are going to bring the omega naught to the outside. And hence this right here is an equivalent expression where this inverse Laplace transform is nothing but the sine of a times t, where our a is omega naught. Meaning this right here is going to be phi dot of 0 divided by omega naught times the sine of omega naught times t. And this right here is basically the solution to our differential equation. This is the most general solution that you can actually get. But physicists can go a tiny little step further. And now we are going to do some magic that you have probably not seen before, most of you, if you have never done nonlinear dynamics or more theoretical physics. We are going to take a look at the phase plane now, because we can actually rewrite this a tiny little bit more using trigonometric identities. It's actually pretty fascinating. I love going at those problems with those methods with the phase plane. It's actually pretty cool. So at first we are going to take a look at our pendulum yet again. If we have our pendulum, okay, swings like this, then our pendulum is going to have turning points, classical turning points. I made a videos on that already and displayed this about classical mechanics. Okay, check it out. So the turning points mean, at the turning points we are going to have no velocity, so no angular velocity overall, because our pendulum is going to stop at some point and then it's going to turn around, okay? Turning points. Meaning the velocity at those turning points is going to be, so phi dot is going to be 0. But what we have here is, okay, when our velocity is 0, our angle phi is going to be at its maximum value, meaning our phi max is going to be at the point where our angular velocity is 0. We're going to have the same situation at this point right here. Okay, phi dot is equal to 0 at phi max. Okay, but then we have another situation. If our pendulum swings like this, and it's basically at the position where our angle phi is 0, it's going to have the highest velocity overall. Meaning at this very point of the pendulum, we are going to have the velocity being at its maximum value. It depends on the direction you are coming at, okay? If it's negative or positive, this velocity actually. But we have that our phi is equal to 0. And we can actually translate this into a phase plane. Meaning we are going to get ourselves a diagram which is going to represent our velocity with respect to our displacement, or just our angle phi, or the other way around. Meaning we can take ourselves the phase plane, and it's going to look like this. We have phi up here and phi dot here, for example. It really doesn't matter, because what we have now is a so-called stable center in nonlinear dynamics. We are going to have a stable fixed point here in the middle, and what we are also going to have is the situations that we have just talked about. If our phi is at its maximum value, our phi dot, our angular velocity, then our angle phi is going to be 0. Same spiel with the other way around. If we are on, so if we approach from this side, we are going to have an angle of 0, and if we approach from this side, we also have an angle of 0, but the velocity are actually different in sign. Okay, sign is turned around, meaning it's going to go through those points. But also, if our velocity is 0, our angular velocity, we're going to have the situation that our angles are at its maximum value with signs turned around. Meaning it's going to trace out in the phase space just a center, a stable center. This is what it's called. It's going to go in this direction, for example, it really doesn't matter. And you have a lot of pendulums, you can draw more onto here. And this is how it's going to go. But we can actually make use of this phase space right now. And I'm going to enhance this a tiny little bit. Let's say we are just going to take a look at the first quadrant. And what we are going to do now is we're going to take a look at initial values. Let's say our pendulum had an initial displacement of, let's say, this right here is our y-coordinate, so this is phi of 0. And at this initial displacement, it has an initial velocity, for example. So this right here is actually going to be just a point in the phase plane, which is going to look like this. But this right here screams for polar coordinates, basically. What we can do is we can draw a triangle into here. And now, what are our side lengths exactly? So what we have here is phi dot with respect to 0. And what we have here is phi with respect to 0. Now the thing is, our hypotenuse is going to be kind of weird right now, because our hypotenuse is going to be the square root of phi of 0 plus phi dot of 0, but this doesn't fit with our dimensional analysis, so the units would be weird. You can do this with the units. So what we are going to do instead is we are going to manipulate our phase plane a tiny little bit more and say that on this axis we are going to have phi dot of 0 divided by omega naught. Okay? So we are just going to play around with the phase plane a tiny little bit more. Meaning overall what we are going to have here as the hypotenuse is nothing but our phi of 0 squared plus phi dot of 0 divided by omega naught squared and the square root of this thing. Okay, if we were to enhance this into another triangle, we're going to get the square root of, and now we are going to give those factors a new name. Let's say this right here is a, and what we have here is b. Okay, just giving it new names. We're going to have a squared plus b squared. It's going to be the hypotenuse. Then we are going to have that this right here is a, and this right here is b. And there's actually a name for this initial value problem, or we can basically give this thing a certain angle. This is the initial displacement, okay, of the problem. We are going to call it phi naught, for example. This right here is just an initial displacement that you are going to have. It's a phase shift, basically. This is what you call it in German, Phasenverschiebung. I don't know what it is in English. It's probably a phase shift. Meaning we actually have some nice connections going on here, and we are going to manipulate this a tiny little bit more. What we are going to do with this equation is we are going to expand this equation by the hypotenuse over the hypotenuse. Meaning we are going to let the hypotenuse be on the outside. Okay, and then we are going to multiply this with a divided by the square root of a squared plus b squared. Then we are going to have the cosine of omega naught times t, and then plus b divided by the square root of a squared plus b squared times the sine of omega naught times t. Okay, so what I basically did is I kept this equation as it is, okay, that's an equivalent reformulation, and multiplied it with a 1, where the 1 is nothing but our hypotenuse over the hypotenuse. And this is actually pretty handy, because you might notice that a over the hypotenuse, that's just opposite over hypotenuse. This right here is the sine of our phase shift, phi naught. So we are going to call this this hypotenuse just a. This is going to be known as the amplitude, okay? You probably know this. And this is going to be the sine of phi naught times the cosine of omega naught times t. And what is b over the hypotenuse? Well, this is just adjacent over hypotenuse, which is going to be the cosine of phi naught times the sine of omega naught times t. And well, now this right here is something, actually What the Heck to subscribe to him, link will be down there in the description, made a video on when talking about complex numbers but different. This right here is just a regular double angle identity. What this, in parentheses, is going to evaluate to is just our sine of those two arguments added together. So we have a times the sine of our omega naught times t plus our phase shift phi naught. And this right here is basically also an expression you could have for your phi with respect to t, if you have a phase shift. But for most purposes, this right here, what we had up here, is actually more convenient because you can plug in the initial conditions directly. But this is what you find in most physics textbooks, and this is where it basically comes from argumentations in the phase plane. Just want to present this to you guys. Also, it could possibly happen that you have phi on this axis and phi dot on this axis. You're going to result in a cosine right here. I think a negative cosine something, and you can absorb the negative sign into the amplitude. Really doesn't matter, it's just playing around. You can always add a factor of 2k pi into here and of k times pi into here and get a cosine out. Really doesn't matter to the phase shift. But yeah, that's basically it. That's all I want to present to you today, and there's going to be more over time. On Wednesday, I believe, we are going to take a look at the general solution to the original problem we had with the sine right here. Includes a very special function which is very dear to my heart, with a lot of approximations. I'm still ill, I'm terribly sorry for that. But this concludes the video. If you did enjoy this little X-course into Laplace Transforms, haven't done this in a while, then make sure to subscribe to the channel. If you did enjoy this video, then also subscribe to Flammy too, doing a lot of content over there. Also, we are going to start with a new playlist soon. And until the next video, I wish you guys a Flammy day. Don't forget to check out STEM Merge 2, and don't forget to check out our sponsor, The Rich. Ciao!